we have now come to the first set of exercises. After our preliminary discussion on how to classify differential equations, we have this. So we will be given some equations and we have to classify each one as ordinary or partial. Also, we have to state the order of each equation, and we have to also say whether it is linear or non-linear. So the first one is this. The given equation is ordinary because the only derivative involved here is an ordinary derivative, not partial derivative. Ideally, we should write is an ordinary differential equation because simply saying that the equation is ordinary may sound misleading, but you understand. Okay. So when you write the solution formally, you have to write the given equation is an ordinary differential equation. I am not going to write that. Then what is the order of this equation? The highest order derivative present here is the first derivative. First order. And is it linear? To see if it is linear, you have to see whether the unknown function, which is y of course here, and its derivatives, there is only one derivative, that do not involve any higher powers than 1, than the first power. Yes, y appears simply as y, not y square or y cube or anything else. Similarly, dy dx also appears to the first power. Also, there is no cross term, that is, we do not see any product of y or dy dx. That is why it is linear. Okay, so that's the first one. Let's see the second one. So here we see third derivative plus 4 times second derivative minus 5 times first derivative plus 3y is equal to sin x. So this time I am going to be even more brief than this one. I will just simply write what it is. This one again is ordinary because only ordinary derivatives are involved. Then the highest order derivative is the third order. So the equation is the third order equation. And what about linearity? Again, although higher order derivatives are there, but each derivative appears to the first power, and also the unknown function y appears to the first power. You do see that this transcendental function sin x of the independent variable, that can be there, but no transcendental function of the unknown function y should be present. I forgot to mention that in this case. I mean, not only should we have the unknown function and the derivative to their first powers and no cross product term, but also transcendental functions of y or its derivatives should be absent. Then only it becomes linear. That is the case here. We do not see sin y, we only see sin x. So that is why it is linear. Number 3, del squared u del x squared plus del squared u del y squared is equal to 0. You can clearly see that partial derivatives are involved here. Also, actually, you just have to see the number of independent variables. In both these equations, there is only one independent variable in each case, which is x. Here, however, we see two independent variables, which is why partial derivatives are appearing. So, this is a partial differential equation. Okay. Then what is the order? Actually, there are two derivatives of both second order derivatives. So, the highest order derivative possible is the second order. So, the equation is also second order. And we only see each derivative to the first power. Also, there is no product of them or transcendental function of them present. And that is why this is also linear. Next, x squared dy plus y squared dx equals 0. It's not exactly given as a differential equation, but I mean it is, but it's expressed in differential form involving the differentials dy and dx. It is equivalent to an ordinary differential equation. First of all, we have to write that. The given equation in differential form is equivalent to the following differential equation, which is x squared dy dx plus y squared equal to 0. Now, I want to say something about the use of these words differential and form. The interpretation of these words here is that it is how the equation looks. In that sense, I am using form. It looks like this. It is in this form that it uses differentials instead of derivatives. However, the term differential form is a technical term. Okay, some objects are there which are called differential forms. That's not what we are talking about here. The equation is in this form which uses differentials, and that is why I am saying in differential form. In differential form, not differential forms themselves. And that is obviously equivalent to this differential equation. So, it is, of course, ordinary, because there is only one independent variable x. First order, because only the highest order derivative is the first derivative. And what about linearity? The derivative appears to the first order or first degree, rather I should say, But the unknown function itself here appears as square. It's not linear. Non-linear. Next, 5. The fifth one is this. This one involves the fourth derivative of y with respect to x plus 3 times the second derivative, but not just simply the second derivative, but its fifth power plus 5y is equal to 0. One may wonder, see, most of us actually already know that these equations arise in many sciences, in economics, in many places these equations arise. They are not simply studied for mathematical curiosity or in their own right. I mean, they are, but they also arise in applications. Now, you may think that such high degree or high order equation may not arise in any applications where, say, you have the fourth derivative, but some differential equations, I don't really know exactly, I have heard someone saying this, that in civil engineering some fourth order differential equations actually arise in applications. Okay, so what about this one? Obviously ordinary. What is the highest order derivative? Fourth. So the equation is a fourth order equation. Is it linear? No, because of this term. Here, the second derivative appears with the fifth power. So this is non-linear. Six. Oh no, it is generally not written as y. U del x squared del y squared plus del squared u del x squared plus del squared u del y squared plus u equal to 0. Two independent variables x and y, so it is partial. Well, you can say, why do you keep saying two independent variable, one independent variable? We can simply see this difference that in an ordinary differential equation we use d and here we use del. That's okay. Just by looking at that you can say immediately whether it is ordinary or partial. But you should not forget what the actual definition is. It depends on the number of independent variables. Okay, so this one is anyway partial. Then what about the order? Order is the highest order derivative present. This is a fourth order partial derivative. Okay, we are done differentiated with respect to two independent variables successively. So you first differentiate u with respect to partially with respect to y twice, and then you differentiate that partially with respect to x twice, but you did it 4 times in total, right? So this is the fourth order partial derivative, a fourth order partial derivative. So that is why this is fourth order. Is it linear? Yes. All the derivatives appear to the first degree, including the unknown function u. So, linear. Next, 6. Oh, this itself was 6, okay. 7. D squared y dx squared plus y sin x. This type of terms sometimes may suddenly confuse us, but we should not get confused. Is it linear? Is it ordinary? Yes. Not first order, second order, because the highest derivative is second derivative. Is it linear? Both the second derivative and the unknown function are appearing to the first degree. You do see, however, a sin x multiplied with y. That's why I said that suddenly it may confuse us. But that's okay. Y is not getting multiplied with some power of y again or some derivative of y. And also we do not see any transcendental function of y or its derivative. There is, however, a transcendental function of x that can be present in a linear equation. So this is linear. But the very next one is slightly different than this one, but looks like this one. D squared y dx squared plus x sin y equal to 0. Ordinary, yes. Second order, yes. But this is not linear, because here we see the transcendental function sin y of the unknown function y. So it cannot be linear. Non-linear. Next, 8. Oh, this itself is it. I keep on forgetting the number. 9. Here the dependent variable is x and the independent variable is t. Usually t denotes time. The fourth derivative times the third derivative plus x equal to t. Okay. Use of x as the dependent variable may suddenly be confusing again, but you do not get confused. Here the function is x or the dependent variable is x and the input is denoted by t. That's all. What is the, first of all we have to say it's ordinary or partial. Ordinary, of course. What is the highest order derivative? Sixth derivative. So the equation is a sixth order equation. Is it linear? No. Because these two derivatives have been multiplied. Their product or this term makes this equation non-linear. this term, I mean, if I want to say so, this term is a linear term. Here the unknown function x appears to the first degree, no transcendental function, no power higher power than the first power, no product of x with any derivative. This one also is a linear term, but the non-linearity comes from here. Next 10. Here the dependent variable is r and the independent is s. It's given in a slightly confusing form. Nice. If you want at this stage, you can go back to the definition of a linear differential equation. In the definition, it was stated that an equation that either is or can be turned into a form like this. The equation in its original given form may have to be transformed into that form which is given in the definition. That's the case here. I mean, you do see a square root here. So this is not the form that we see in the definition of a linear differential equation, but it can be replaced with an equivalent differential equation that is in that form, or more simply put, it can be turned into that form. The given differential equation is equivalent to the following, which we obtain of course by squaring both sides. dr ds. So if we square, the left hand side will be a sixth power and the right hand side will be d squared r ds squared plus 1, or if you want you can bring all those things to the left hand side. Oh, and also write the equation in this form where we first write the highest order derivative. So minus d squared r ds squared plus dr ds to the power 6 minus 1 equal to 0. Okay. So the equation given equation, because whatever we are going to say about this equation, the same is going to be true for this one as well, because they are equivalent, is ordinary you may have one problem here or may have a confusion here. Squaring both sides gives us this, but from here can we take square root on both sides to have this? That is your problem. Maybe that maybe this becomes negative at some point, but that cannot be true because the given equation itself involves the radical. So the function r, which is a function of s, is such a function that in its domain this second derivative plus 1 never becomes negative. With that understanding, these two equations become equivalent. Just like you can get this one from this one, you can also go back. Is ordinary second order, because the highest order derivative is the second. And is it linear? No. This term is non-linear because it involves the sixth power of this derivative, first derivative. Okay, so that's just it. That is this exercise set. From the next section onwards, we are slowly going towards what a solution even means, how to find solutions to some specific types of differential equations, and how linearity is going to help us in finding solution. Linear equations, we have already mentioned, are easier to solve than non-linear ones. So gradually we are going to get to these parts. So that's just it for tonight. Oh, and tomorrow let us do class 11 trigonometry. I have decided to keep Mondays only for number theory and Wednesdays only for class 11 mathematics, because otherwise the gap between two videos becomes just really too long. So that's just it for tonight. So see you tomorrow with that, with trigonometry. And until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.